Hi everyone. Today we're going to resume our series on translating functions from data.list into length index vectors. So this is an exploration of type level programming in Haskell. And so the past couple of weeks we've started to build up all of these functions. By the way, the code that we're going to see today is posted online. There's going to be a link down in the description. And so this is our fourth week of doing this. So far we've seen how GADTs work a little bit, we've seen how singletons work a little bit, and we've seen how type families work a little bit. Today's subject is going to be existentials. And before you get scared off at the long time on this, there's going to be sort of a natural breaking point. We're going to do a simpler example, and then I want to do a little bit more of a long, drawn out example. But if you just watch the first half or so, then that will be good enough. Okay, so let's dive in. Oh, and by the way, you don't need to watch previous videos to be able to understand this one. I try to make them each sort of independent. The key definition is the one that we see on the screen right now. And actually, what I'm going to do is let me keep that up on the screen, and let me see if I can get Emacs to do this. I think that might do it. There we go. So now we can keep that up there, and then we can just work down here. This will be enough space. And the function I want to look at today is, where is it? Is filter. So let's take a look at filter. So if we think about filter on lists has a very nice type. Looks like this. And the idea here is that we're going to get a predicate of type A arrow bool, and then we want to keep all of the elements in this input list that meet the predicate. The challenge with length indexed vectors, though, is that we don't know how many elements in our vector are going to meet the predicate, so we can't say how long the output is going to be. Right? If I just do a naive encoding like this, well, that's not going to work out so well because my output length, n, is not going to be the same as my input length. So I'm going to say, okay, so fine, let's just make the output length different. So let's actually write this. So we're going to get a predicate p, and let's see, if it's empty, then we'll just return empty. That's easy. Oops, I don't call it that. That's very silly. I call it this. And then we don't need that p. And then here, if we have x cons x's, then if px holds, then we want to keep x. So we're going to do x cons filter px's. And otherwise, otherwise we're going to go just filter px's. Okay, there we go. Now if I try to compile this, I get an error. Oh, not in scope otherwise. Oh, well, that's very silly. A lot of people think otherwise is a keyword. It's just defined to be true. Let's see if we can get a more interesting error down here. Could not deduce m equals suck n0. Is there anything? Is this one simpler? Oh, yeah. Let's just use this first one. Could not deduce m equals 0 from the context n equals 0, right? So it's looking like I'm saying here that n and m are going to be two different lengths, and they are different lengths. But the way that all of this stuff works is that n and m are both chosen by the caller. We can think of n and m, and a for that matter, as extra parameters to the filter function. So every time we call filter, we have to choose what is a, what is n, and what is m. Most of the time, GHC just does this choice for us. We don't really have to worry about doing it. But if we think about these as inputs, well, there's nothing that says that this result type m is going to be 0 just because the input is 0, right? There's nothing tying these two together. On the other hand, we do know that n is 0 if the input is empty. Oops, we've lost vec up here. Let's take a look at it again. Right, if we've pattern matched on nil, then we know that n has to be 0. So that's all well and good, but we don't know anything about m. So this type is just not going to work out for us. Instead, what I want to do is I want to say that there exists some m such that the result is going to be vec ma. And this is in contrast to sort of the default quantification in Haskell, which is for all, right? So we're going to say that this works for all NA, that we take these inputs and then we're going to produce some vector vec ma such that there exists m such that we get this result. The problem is that exists, well, it doesn't. So today in Haskell, we can't write exists the same way that we can write for all. But I'm actually going to have a link in the description. There's a paper that I've submitted for ICFP. Early reviews are looking positive, so I'm hopeful that it's going to get accepted into ICFP that actually describes a way we can work exists into the language. So there's going to be a link for that in the description. I don't want to focus on that too much today, especially because my implementation isn't quite working yet. So this isn't going to work. Instead, what we have to do in Haskell is to define a separate data type that just deals with that deals with sort of this existential quantification. So I'm going to call it evac. So we're going to have evac here, and let me give a type signature. So it's not going to take a length, it just takes the type of elements. So evac a, where mc_evac is going to take some vec na and pack it into an evac a. Note that this result does not mention n. That's what makes n existential here, is that we're sort of taking it and packing it inside of our data type so that we can't see it from outside. So then now here, instead of exists m business, I just say evac, and then, oh, I don't have a length at all. Okay, so let's see, does this work? Well, no, not quite. And that's because nil is still a vec, not an evac. So I have to wrap this in mc_evac here. Now, does that work? Well, we've made some progress. Now, that works here, good. And let's see, so again, couldn't match. So we need to call mc_evac again. But we still get a type error because here the result of cons, well, that's going to be this recursive call to filter, and whoops, I don't know what that is. Right, because the result of filter is going to be an evac. I can't just cons onto an evac. So we have to somewhat painfully run this through separately. Then we're going to pattern match on this, and then we have to unwrap this mc_evac constructor, and then we'll call that tail. And then over here, we have tail. Aha, and now it works. And we don't have to do this in this case because we're getting an evac and we're returning an evac. So we're just not going to bother wrapping or unwrapping. So this is a bit painful here, but unfortunately, this is about what we have to do to work with existentials. It could be tempting, for example, to try to use a let binding or something like that, but lets don't really work with this. I don't want to explore that right now. That'll be a bit of a diversion. But here, this is really how we'd have to do it. The other really unfortunate thing is that this rewriting, just to appease the types, also changes the strictness of my filter function. Right? A typical filter function on lists produces the output sort of as it consumes the input. And so that way we can do things like list fusion, and in a lazy language, we get good things happening. Here with this filter, we have to evaluate the whole filter, the whole output, before we start consuming any of the input. So that's not very cool. But that's also addressed in the paper, and we can see how some of these new ideas in this paper have a way of making a lazy filter over length index vectors, which is kind of cool. So looking at this, actually, we can still do better. And the reason we can do better is because we know something about the output length. It's not any length at all. That length can't be any greater than the input length. So I want to go back and I want to take a look at this evac and see, can we do better? So specifically, instead of just quantifying evac over the type, I want to quantify it also over a constraint on the length. So we're going to take some constraint, right? Constraint, essentially a class constraint. We'll see an example of this in just a minute. And it's going to take in a nat, and this is how we can say that the output is going to be less than something. So what we're going to really say is that whatever this length is of this list inside of my existential, it has to obey this constraint. So let's call that constraint C. So the result is going to be C here. And the constraint is going to be that C applied to this n must hold. Okay, let's just see if that so far makes sense to GHC. Oh, we don't know what constraint is. That's easy to fix. We just import it from data.kind. Okay. Oh, and now we need constraint kinds. Aha, that works. Okay, let's get the type back up here. Whoops, don't do that, do that. Okay. So then here we are. Now we have some arbitrary constraint. Well, now our filter, now we're going to get all kinds of problems because we don't have an arbitrary constraint here. So the first thing that we're going to try is let us just have an arbitrary constraint. In other words, one that's always satisfied. So we're going to have class, know nothing, because we know nothing about this nat. And we're just going to have an instance, know nothing. Oh, but this know nothing is nat arrow constraint. And then now I can write know nothing here. And I think everything should be well. Oh, no, it doesn't. Everything is not well. Why? Oh, haha. Flexible instances. Sure. I'll put on flexible instances if you ask me to, GHC. Aha, yes, excellent. So what we're saying here is that this know-nothing constraint is true for any nat n. So here, this particular result, well, we know nothing about it, that's fine. But that's not very interesting, is it? Instead, you know what, I think we're going to get rid of this up here because now it's getting more interesting down here. So I don't want just this know-nothing, I want a less than constraint. So we're going to have a type less than nat to nat to constraint. But actually, we need to be careful here because what I want to say is I want to say that the second one is less than the first. So if the second one is less than the first, we normally spell that greater than. But actually, I don't really even mean the second is less than the first. I mean the second is less than or equal to the first. So I really want this type here. And this is going to be a class, m greater than or equal to n. And it's going to have some instances. So we're going to have an instance, m is greater than or equal to 0 for all, no matter what m is. And then we have another instance that if m is greater than or equal to n, then that implies, let's use some parentheses here for easy parsing, then that implies that suck m is greater than or equal to suck n. Okay, how are we doing here? Oh, multi-param type classes. Sure, why not? Okay, excellent. Okay, and we'll jump back down here. Excellent. So now we have this. Now, instead of just saying evec know nothing, I know that this is going to be true. So it kind of looks like I'm saying greater than or equal to n, right? But this is just a way of saying I'm going to partially apply this class to n. So n is actually the left argument. So we're really saying that n is greater than or equal to, well, whatever the length of this existentially quantified vector is. Now let's see, does this work? Not so easy. Cannot construct the infinite type blah. So the problem here is that I know that this returned filter, well here, what I know about this returned evec is that its length is less than or equal to the length of x's, but I don't yet know that it's less than or equal to the length of x cons x's. The way to solve this is fairly easy. We just have to pattern match on it and then rebuild it. And this gives GHC, this pattern match and rebuild gives GHC a chance to sort of twiddle my type parameters. And now maybe, oh, no, still doesn't work. Could not deduce blah. Could not deduce blah. Let's think about this. Okay, here we're going to have some live thinking. Could not deduce that suck of n1 is greater than or equal to n2 if n equals n1 and n1 is greater than n2. So let's just think about this for a sec. So if n equals suck n1, then we know that n is greater than n2. Oh, but there's something else going on here. Let me just think about this a moment. Aha. So what this is really saying is that here I've given sort of two axioms for greater than or equal, but neither of them fits my need here, is that I know that n1 is greater than or equal to n2. I get that from the recursive call to filter. But what I don't yet know is that suck of n1 is greater than or equal to n2. And so let me add another axiom. Let's see, does that work? So if I know that m is greater than or equal to n, then I also know that suck m is greater than or equal to n. Does that work for me? Oh, but now we get overlapping instances. Well, it turns out that if an instance here doesn't really have any methods, the fact that it's overlapping doesn't matter. I've given multiple ways of proving greater than or equal to. They're all fine. So I can just mark this as overlapping. And does that solve the problem? Oh, it still says overlapping. I think that I meant overlappable. Aha, now that works. So this is a bit sketchy here using overlapping instances, but in reality, if I did really care about this, I could write a proof. We'll see that in a future week. But here now, look at what I've done. So now I've taken filter, it works over a length index vector. The result I get out, I could pattern match on it to get a length index vector out, and I know that the length of that vector has to be no greater than the length of the input vector. So that's pretty cool. So I already have all this information about filter. I promised at the beginning that we're going to have sort of a time to leave. Now is the time to go if you want to. But what I want to do next is I want to try something a little harder, and I want to see what progress I can make defining union. That's going to be our next step. So let's jump to it. So if we scroll down a little bit, I have union in my list of possibilities, and let's see what we can do here. So union, and this is going to be a little bit of live thinking. This might go a little slower. I have not pre-cooked this. So let's see, union, we're going to take in a vec NA and a vec MA. These really are two different inputs, so they can be different types. That's fine. And what's the output going to be? Well, it's going to be an evec. We don't know the length of the output, but we do know that it's going to be, the length has to be, well, it has to be greater than or equal to n, but of course I have to spell that like this because there's no sections at the type level. So it's going to be that, but it's also going to be greater than or equal to m, like that, I think, something like that. And this isn't really anding two bools, it's sort of anding two constraints. So I'm going to write it kind of in funny brackets like this. So let's leave that there for now. And now we can define these extra operators. So we're definitely going to need type less than or equal. So that's going to look like this. And so the class, let's see, that's going to be m less than or equal to n. And then 0 is less than or equal to anything. And if m is less than or equal to n, let's do some parentheses here, then suck of m is less than or equal to suck of n. We might need more axioms, maybe some overlapping stuff in a little bit. And let me recenter. Okay, cool. Oh, and we don't have the and thing. So let's see, the type of this and thing, it takes two nat arrow constraints and produces a nat arrow constraint. Okay, so that's our and operator. And this is going to be another class combining two conditions. And the instance is going to be, well, that both conditions hold. It's and. So I want the instance to be, so if cond1n holds and cond2n holds, well then cond1 and cond2 of n holds. So let's see what we think about that. Oh, it doesn't like that. There's some problem. Couldn't match expected kind constraint. Oh, haha. That's because really there's still this n here, right? This is sort of like composition of functions, right? We can just sort of define things this way. This actually works. I can do slightly better. Well, we're going to come back to slightly better. I think we'll need to be slightly better in a few minutes. Okay, so now that we have this all defined, let's actually define our function. So here, well, it's very simple. So if I have x's and empty, then that's just x's. Let's see, can we get that accepted? Oh, couldn't match. Oh, we don't have an evec. So we'll make evec here. Let's see. Now we're going to complain about other things. Could not deduce that n is less than or equal to n. Well, none of these axioms directly imply it. We can figure that out by an inductive reason, but GHC isn't smart enough to do induction on its own. So let's just tell it that for all n is less than or equal to itself. We're just going to declare this to be reflexive. And now there's probably overlapping instances, and that's fine. And then we can just mark this as overlaps, just to make our lives simpler. Oh, still overlapping instances. Oh, because we don't know about 0. Let's just mark up all overlaps. I don't really care about overlapping. Let's just make the problem go away. Will that make the problem go away? Oh, bah, still won't go away. So what it's really worried about is that if we have something that is, if we have something here that's 0, right? I don't know if I should use this first instance or this last instance, because 0 equals 0, 0 less than or equal to 0 can be proved in two different ways. So my inclination is just to scrap all of these axioms and instead use the ones that are more useful to me. So I'm going to say that any number is less than or equal to itself, including 0. And if n is less than or equal to m, then then I know that n is less than or equal to suck m. And this is just a different axiomatic way of doing less than. Let's try this. That might work better. Still overlapping instances. Oh, phooey. Why is this still overlapping instances? Overlapping instances for n less than or equal to m. Oh, but these aren't. That's not true. Can I fix this with overlaps now? If I mark this with overlaps, I was able to do this at one point in my history. Okay, in the interest of making forward progress, I'm going to take out the sledgehammer. Beware the sledgehammer. This is the sledgehammer. Incoherent instances. Go away, pesky errors. Oh, no, you didn't. Still overlapping instances. To pick the first instance above, use incoherent instances. I did that. Did I spell it right? Yes? What's going on here? Oh, maybe I have to get rid of the overlaps because it thinks I'm being careful so that it doesn't want to use the incoherent thing. I don't know. Is there something very silly I'm doing? Oh, haha. Oh, wait, no, that's... what's going on here? Could not deduce 0 is less than or equal to n. Well, what if I just say that? Oh, now it's working. But that was a very silly error. I bet that's a bug in GHC. Bad GHC. Okay, let's carry on. So here, let's see, we have union... we have one equation. Okay, that's not very interesting. Let's try another equation. Mc evac of y's. Oh, good, that still worked. But of course, now we have the hard case, the cons case. So here we have x cons x's and y cons y's. And now it really depends on whether x equals y or not. Or wait, or does it? Let's think about this. So if I want to do a union of things, no, I don't want to match on both of them at the same time. That's very silly. Instead, what I want to do is I'm going to sort of insert the x's into the y's one by one. And so here what I want to say is I want to say that I want to insert this if x's is not in the y's. And so I can do that by saying, well, I'll do it the other way around. If x lm y's, then I don't want to add it. And then I just want to compute union x's y's. Oh, I'm going to get tons of type errors soon. Yay. Otherwise, if x is not in there, then I want x cons on the union of x's and y's. And I think that's about right for union. So let's see what happens here. So we're going to say, oh, we don't know what lm is. Well, lm is luckily easy to define on vectors. So lm is vec a, vec na to bool, because the result is just bool. So I didn't bother to define this earlier, but let's do it now. So we have lm of x, and in the empty list, that's always going to be false. If x is in y cons y's, well, that's true. If x equals y, then that's true. Otherwise, what do I want to do? Oh, I check if lm is in here. And, you know, from teaching Intro to Computer Science so many times, Intro to Programming so many times, I can't stand this. So let's fix this. This I really want to say equals or. This is why we have or in the language. Okay, so it's either x equals y or x is an element of the tail. Okay, now we're going to get a whole ton of things. Let's just make sure we don't have precedence errors. I don't think so. Variable not in scope equals. Well, of course, that's silly. Let's just bring that into scope like that. Oh, and now, of course, or isn't in scope. And now what do we have? Okay, couldn't match type. Oh, wow, lm worked. Hey. There's going to be a problem with lm. Perhaps you see it. We'll have to return to it. But now we have a couldn't match vec and evec. Well, that kind of makes sense, right? Because, let's see, where is the error happening? It's right here because this union is returning an evec. So we have to play the same game that we played before. So let's do case union x's y's of mc evec u for union. And then this is just going to be x cons u. And, oh, up here, oh, occurs check. Now we have the same problem that we saw earlier when we just try to sort of pass something through. It's because the type indices are changing. So again, I have to do this kind of thing up here. And this is just going to repack it. Okay, let's see. Now what do we get? Oh, now once again, this is a vec, but we need an evac. Yuck. So we do this business. Oh, now we get other errors. Okay, this was the error I was hoping to get a little bit earlier, right? Of course, we need an eq instance up here. That's easy. I can write that in, right? Still, the old things still are true. Right? We need eq instances to compare for equality. And now we're down here. Oh, and of course, we need an eq instance on union. You're probably sitting there wondering, where's that eq instance coming from? When are we going to need that? Well, that's when we do. And let's see what else. Now we start getting the more interesting things. So I'm going to need to look at this type error a little bit more intensively, so we need more space. So M could not deduce that M is less than or equal to M2 from a whole bunch of other stuff. So here we know that M is less than or equal to M2 because that's what this means when we combine these two constraints here. This is where I'm looking. So we see here that M really is less than or equal to N2, but yet could not deduce that M is less than or equal to N2. And the reason for that is that we know all of this thing, we know this conjunction, but we don't know that the conjunction implies the conjuncts. So what I really need to do is I need to tell GHC this by adding a class constraint, right? This instance means that if I know the individual pieces, I can conclude the conjunction. But I haven't said that if I know the conjunction, I can conclude the individual pieces. So let me put that in. So I can do that by writing cond1n, cond2n as a class constraint here, essentially making this ampersand operator just a conjunction of these two pieces. But I can partially apply it as I've done here, so it's really more powerful than just the sum of its parts. So now I compile, undecidable superclasses. That's because, of course, cond1 and cond2 might somehow refer to and again. But let's just break out yet more extensions, undecidable superclasses. And then now we get other errors. Let's see, what do we have here? Okay, so now we can't deduce that suck n1 is less than n2 from n1 is less than n2. Well, that actually appears to be quite sensible. If I know that n1 is less than n2, I don't know that suck of n1 is less than n2. Do I have any other information? Why is this happening? That's because I'm saying that the output result has to be at least the length of both inputs. But this, oh dearie me. Oh dearie me. Let's think about this a moment. First off, is this true? Is the thing I'm trying to prove a true fact? I think it is. I think it is. Oh, but it's not really true, right? If my first input is, say, a vector of 10 threes, and my second input to union is just one lonely 3, then indeed my output will not be greater than the length of my first input. That's kind of sad, but I think that might be true of the built-in union. Let's find out. If I say import data.list, now if I say data.list.union of 3333 and just the list 3, oh, that happens. Maybe this one is built the other way around? I don't really know what's going to happen here. Aha! So the built-in one inserts the right one into the left one, clearly. And so my initial condition was wrong. I don't want to improve necessarily on what happens in the standard library. I could try to think of a way of making this true. We would have to have some uniqueness constraint on the inputs or something crazy like that. But for now, I'm just going to delete this extra piece because it's wrong. Wrong things are bad. So now let's try this. Oh, it worked. Haha. Did not use X. Why did I not use X? I don't like any errors. Look at that. So that was a fun little exploration. We didn't quite get what we wanted to, but we learned something along the way. I think we'll hold it there for now. Next week, we'll actually see proper proofs that are needed to define some functions over these length index vectors. I hope this has been fun to watch. Thanks very much for watching. Bye.